For a black hole that is currently feeding, perhaps devouring a companion star, or in the case of quasars, a bunch of its host galaxy's gas, the ISCO is expected to eventually be detectable as a dark circle in the middle of the otherwise insanely bright accretion disk formed by the infalling matter. And that's because any gas that gets close will quickly be swallowed by the black hole. To date, ISCOs have not been directly detected, though there is tentative evidence in gravitational lensing studies of quasars. So yeah, you can orbit safely pretty close to the Kerr black hole's event horizon. Just above the event horizon, we find a particularly bizarre region called the ergosphere. There, frame dragging carries space around the black hole at faster than the speed of light. That means everything, even light, must move in the direction of the black hole's spin. The situation here is actually similar to the state below the event horizon, where space moves downwards faster than light. In the math, that faster than light flow of space is represented in a particularly weird way. Space and time switch places. In particular, the radial direction becomes time-like, so downward motion becomes as inevitably one-directional as time. Well, in the ergosphere, the angular coordinate becomes time-like. It's as difficult to resist orbiting the black hole than it is to travel backwards in time, which is to say it's impossible. That same switch also allows us to extract energy from the ergosphere, as we'll see. The ergosphere extends all the way down to the event horizon. Now, the event horizon in the rotating case is not spherical, it's squished at the poles like the rotating Earth. More spin means more squished. The ergosphere has a similar shape, but also dips at the poles to touch the event horizon. It's sort of pumpkin shaped. Now, I know you would love to just drop below the event horizon right now, but you're going to have to wait. There's still plenty to do in the ergosphere, like building a hyper-advanced black hole engine. The great Roger Penrose figured this out in the early 70s. It goes like this. A massive object is dropped into the ergosphere of a Kerr black hole on a carefully tuned trajectory. If the object is split into two pieces at exactly the right point, one half will go plummeting through the event horizon, while the other is ejected from the ergosphere and escapes. In fact, it escapes with more kinetic energy than it had coming in, up to 20% of the energy that was bound up in the mass of the half that was lost. This energy is extracted from the rotational energy in the ergosphere, slowing the black hole's spin. To get more technical, it works because the weird space-time flip in the Kerr metric of the ergosphere allows one half of the object to acquire negative energy, which is transferred to the black hole, while the other half gains the difference in energy as kinetic energy. So there's your black hole engine. Maneuver rocks into a Kerr black hole, blow them apart at the right time, and catch the kinetic energy of the pieces that get ejected. Sounds a little messy actually, but you can do this with light. Light that is directed through the ergosphere in the direction of rotation will also extract rotational energy and emerge amplified in a process called superradiance. This way, the rotational energy can be extracted with, in principle, 100% efficiency. Oh, and you can also build a black hole bomb this way, by surrounding a Kerr black hole with mirrors. Then you just shine a flashlight at the black hole, and its photons pass through the ergosphere again and again and again, becoming exponentially amplified, until boom. The last process we'll talk about is actually important in the real universe. It's the Blandford-Znajek process. In this case, you have a magnetic field produced by the flow of material around the black hole in an accretion disk. The flow of space in the ergosphere spins up the magnetic field into a gigantic particle accelerator. Charged particles are accelerated along those magnetic field lines and can radiate intense light. Ultimately, the energy of that light is extracted from the rotational energy of the black hole. It's hypothesized that some jets observed from accreting black holes may be powered by this process.
All right, well, we've got to start with the research paper that caught everybody's attention this month, which was this from Seiyo and collaborators, which claims that the star Betelgeuse could go supernova in the next few decades. You heard me. Decades, not centuries, not millennia or millions of years, you know, the usual astronomical timescales that we deal with, but decades. And yes, before the inevitable comments roll in, Betelgeuse is over 600 light years away, so it could have already gone supernova, but the light hasn't actually had enough time to travel to us here on Earth yet. But we're talking about in Earth's frame of reference, right? The light that we are receiving now suggests that we could be seeing the light from a supernova in a few decades' time. But before we get too excited, let's chat about where this claim comes from. What is the evidence that they have here? Well, it's all to do with how Betelgeuse's brightness changes. But it's nothing to do with the Great Dimming event, where Betelgeuse's brightness abnormally dipped by a huge amount from December 2019 to February 2020. I actually covered it at the time in a Night Sky News episode, and then again in another Night Sky News episode from August 2022, when a study was published claiming that this Great Dimming was due to a big ejection of material from Betelgeuse's surface. But along with that very unexpected change in Betelgeuse's brightness, there's also a lot of regular changes in Betelgeuse's brightness that we're aware of thanks to decades of observations. So there's a few patterns in the changes to the brightness that aren't quite as dramatic. There's two main ones with patterns that repeat every 2,200 days and every 420 days. And then there's two that are just a little bit harder to pick out from the data that happen every 230 and 185 days. These changes in the brightness are essentially caused by pulsations in the star due to this endless fight between gravity pulling inwards and then the energy from nuclear fusion and the gas pressure pushing outwards. So if you make a model of Betelgeuse the star at its mass and its size, you can start working out, okay, well, what conditions inside the star would be responsible for making these pulsations of every, 2,200 days and 420 days, etc., etc. That's what Seiyo and collaborators have done here and found that to explain these pulsations, Betelgeuse can no longer be fusing hydrogen into helium, but instead fusing carbon atoms together to make heavier elements like neon or magnesium. So if you think about what's going on in the interior of a star during its lifetime, you need incredibly high temperatures and incredibly dense pressures for fusion to take place, just to bring hydrogen atoms close enough together to get them to make helium. That only happens in the very core of the star. That's the only place that it's hot enough and dense enough. So during a star's, normal lifetime, it will just slowly be converting all of its hydrogen in that core to helium. At some point though, all of that hydrogen will run out and you'll just be left with a pure helium core. At that point, there's no process producing energy that's going to push outwards against gravity pulling inwards. And so then the star starts to shrink in on itself. But when that happens, the core then gets hotter and denser, so much so that you can then trigger helium fusion into carbon. Of course, then when all the heliums run out, you then got a carbon core and the star shrinks again, but then you kickstart carbon fusion into neon and magnesium, and so on in this sort of like shrinking and more fusion process until you get to silicon fusion into iron. At that point though, fusing iron together to give you a heavier element gives you less energy out than you have to put in to get the iron atoms together. And that's when there's no other process to resist that crush of gravity and you get a supernova. All those outer layers of hydrogen collapse in, rebound off the core and out into a beautiful nebula. And then depending on the mass of the core of the star in the center, you either get a neutron star or a black hole left behind. Now, all these different stages of fusion, so hydrogen fusion, helium fusion, carbon fusion, they all last for a different amount of time. The hydrogen hydrogen fusion is the longest. And for a star like Betelgeuse, it'll probably spend around about 11 to 15 million years fusing hydrogen into helium. Whereas a less massive star like the Sun will spend about 10 billion years fusing hydrogen into helium. The carbon fusion stage, though, is much shorter than the hydrogen fusion stage. And again, it varies slightly for the mass of the star that you have, but it's more like hundreds of years rather than millions or billions of years. Seo and collaborators actually looked at the fraction of carbon left in the core in each of their models that they used to explain the pulsations in the Betelgeuse's brightness, and found it was very low, always less than 20%, suggesting a good chunk of the carbon in Betelgeuse's core could have been used up already, and the star is nearing full-on collapse, aka a supernova. Seo and collaborators also took one of these models and plotted how long it would be before the collapse, given the fraction of certain elements in the core. So this is a log plot, so on the x-axis here, a 5 means 100,000 years, aka a 1 with 5 zeros after it. 0 means 1 year, i.e. a 1 with no zeros after it. And -5 means 0.00001 years, i.e. a 1 with 5 zeros before it in the decimal point. So you can see in the black line there, that's the amount of hydrogen, and it drops as the amount of helium in the gray line goes up. But then helium starts to go down as more carbon in the red line there is made, and that goes up, and so on and so on. And as we just saw, the models that can reproduce Betelgeuse's pulsations in its brightness found that the carbon fractions were between 17% and about 0.5%, putting their best models for Betelgeuse in terms of how long it is before collapse between 1 and 2 on this log plot, meaning that there's somewhere between 10 and 100 years before Betelgeuse's collapse. Again, decades, not centuries, not millennia, decades in our lifetime. And this is what's got people so excited. The last supernova in our galaxy, the Milky Way, was back in the 1600s. So to have the opportunity to study a supernova that is that nearby as Betelgeuse is, around about 600 light years away, and the opportunity to study the remnant that's left behind, so the neutron star in the core after the supernova, and then of course the opportunity to actually see it yourself in the sky, for the Orion constellation to look so completely different from then on. And then also maybe even see it in the daytime sky as well, because it's that bright that you can see it despite the fact that the sun is so bright. It's just too exciting. Now, of course, these are just best fit models, and that comes with a lot of uncertainty. So we do have to bear those caveats in mind. And of course, it is all still speculation until Betelgeuse actually does go supernova.